To factor this expression, we're going to look for a greatest common factor between the two terms. For the number factors, we've got a 5 and a 10. So our greatest common factor in terms of numbers is 5. For the variable factors, we look for the lowest exponent for our factors with an x as a base. And the lowest exponent is negative 5/4. So x to the negative 5/4 will be in our greatest common factor. To get the leftover factors, we're going to take each of the terms and think of what happens if we divide them by 5x to the negative 5/4. The first term is pretty simple. 5x to the negative 5/4 divided by itself is 1. For the second term, 10 divided by 5 is 2. And then for the variable, we're going to think about what x to the 1/4 divided by x to the negative 5/4 is. If we're dividing and our bases are the same, we subtract the exponents. So x to the 1/4 divided by x to the negative 5/4 is the same thing as x to the 1/4 minus negative 5/4. 1/4 minus negative 5/4 is 1/4 plus 5/4, which is 6/4. And we can simplify that exponent to 3/2. So x to the 3/2 is the variable part that's left over when we factor out our greatest common factor. One more step and we'll be done. We have a factor that has a negative exponent on it, and that's the x to the negative 5/4. To simplify this, we need to take that x to the negative 5/4 and move it down to the bottom of the fraction so that it has a positive exponent. The 5 does not have a negative exponent, and the 1 plus 2x to the 3/2 also does not have a negative exponent. So we've got our final answer. To solve an equation with a fraction in it, we can clear out those fractions if we multiply both sides of the equation by the least common denominator of all the fractions, which, because we have a 4 and a 9 in denominators, would be 36. So we're going to multiply everything on both sides of the equation by 36. When we do that, we'll be able to simplify each fraction. On the left side, we know that 4 goes into 36 9 times. So we're left with 9 times x plus 5. On the right side, we've got 36 times 1, which is 36. And then when we distribute to the fraction, 9 goes into 36 4 times. So we're left with minus 4 times x plus 1. We'll distribute 9x plus 45 equals 36, and distribute over here. Negative 4 times x is negative 4x. Negative 4 times 1 is negative 4. We'll go ahead and simplify the right side a little bit more, because we can certainly take 36 and subtract 4 from it and get 32. Let's get our variable terms to the left side. So we'll add 4x to both sides of the equation. That will give us 13x plus 45 equals 32. We'll subtract the 45 from both sides of the equation to get the constant terms on the right side. So that'll give us 13x equals negative 13. And then divide both sides by 13, and we get x equals negative 1 for our solution. Here's another equation with fractions. We're going to do the same thing. We'll multiply both sides of the equation by the least common denominator, which would be the x plus 2. So multiplying the left side by the x plus 2 and multiplying the right side by the x plus 2. On the left side, when we multiply the x plus 2 times the first fraction, the x plus 2's cancel and leaves us with just a 3. When we distribute to the 3, that leaves us with a 3 times the x plus 2. And on the right side, the x plus 2's cancel, leaving us with 15. On the left side, we'll distribute the 3, so 3x plus 6. We'll combine our like terms on the left side. 3 plus 6 is 9, so 3x plus 9 equals 15. Subtract that 9 from both sides, so 3x equals 6, and then divide both sides by the 3 to get x equals 2. Now there's one more thing we need to check before we are convinced that this is the solution, and that is we need to look to see if we have any restrictions on the variable. Restrictions are numbers that make any of our denominators equal to 0. And since we have variables in the denominators, we will have restrictions. X plus 2 is in our denominator on the left side and the right side. So if we'd like to know when is x plus 2 equal to 0, that's when x is negative 2. That is a restriction on our solution. We did not get negative 2 as our solution, so 2 is a valid solution. It's not a restriction, so it's a solution. Now let's solve this equation. It's a little simpler equation, so it shouldn't take us quite as long. On the left side, we'll distribute the 4, giving us 4x plus 12. On the right side, we've got 3 plus 4x. If we get our variables together on the left side, we'll do that by subtracting the 4x from both sides, and that gives us the statement 12 equals 3. That's a false statement. That tells us that our equation is going to be false no matter what number we put in for the x. So our solution is there's no solution. We can write no solution by writing no solution, or we can write the empty set symbol. We are asked to determine whether the equation is an identity, a conditional equation, or an inconsistent equation. If we get a statement that is false, then we say that we have an inconsistent equation. If we had a statement in which all the variables drop out, but the statement is true, like 0 equals 0 or 5 equals 5, that would be considered an identity. And if we get a solution, x equals a number, that's called a conditional equation. For our next problem, we're multiplying two imaginary numbers. So we'll do that by what you probably think of as FOIL. We'll multiply the first terms together. Negative 3 times 7 is negative 21. The outers, negative 3 times I is negative 3i. The inners, 2i times 7 is 14i. And the last times the last is 2i times I, which is 2i squared. The outers and the inners are like terms. We'll be able to put those together. So negative 21 plus 11i, and then I squared is negative 1. So the last term, 2 times negative 1 is negative 2. And then finally, we can combine the negative 21 and the negative 2 to give us negative 23 plus 11i, and we've got our final answer written in standard form. To divide imaginary numbers, what we'll do is multiply the numerator and denominator by the conjugate of the denominator. The conjugate of 3 plus 6i looks exactly like that, except we change the sign. So the conjugate of 3 plus 6i is 3 minus 6i. And we're going to multiply the numerator and denominator by the same 3 minus 6i so that we don't change the value of this fraction. In the numerator and denominator, we're going to have to multiply the binomials. So in the numerator, first times first, 2 times 3 is 6. Outers, 2 times negative 6i is negative 12i. Inners, 6i times 3 is positive 18i. And then last times last, 6i times negative 6i is negative 36i squared. In the denominator, we'll multiply the same way. So first times first, 3 times 3 is 9. Outers, 3 times negative 6i is negative 18i. inners, 6i times 3 is positive 18i. And last times last, 6i times negative 6i is negative 36i squared. Now we'll look for some like terms to combine. In the numerator, we've got a 6. Negative 12i plus 18i is 6i. And then I squared is negative 1, so negative 36 times negative 1 is positive 36. In the denominator, we have a 9. Negative 18i plus 18i, those are opposites, they add to 0. And then negative 36i squared, I squared is negative 1, so that's negative 36 times negative 1, which is positive 36. In the numerator, we've got 6 plus 36, that's 42, plus 6i over 9 plus 36, that's 45. Now we'll write that as two terms, since we have that common denominator. So we have 42 over 45 plus 6i over 45, and now let's simplify the fractions. First fraction, we're looking for a common factor. We've got a 42 and a 45. 3 will go into both of those. 3 goes into 45 15 times. 3 goes into 42 14 times. So that's 14 fifteenths. And then in the second fraction, 3 goes into 6 twice, and 3 goes into 45 15 times. So we have 2 fifteenths times I. So now we have our answer in standard form. For the next problem, we're going to do this division and write the result in standard form. The thing to notice is that we do have a negative number underneath that square root. So we are going to have an I as part of our answer. In fact, let's deal with that right now. So when we look at negative 20, 20 has a factor of 4 in it, which is a perfect square. The square root of 4 is 2. And it has a factor of negative 1. Square root of negative 1 is I. The leftover factors would be just a 5. Remember, we took a 4 out of the 20. That leaves us with a 5. We took the negative 1 out because the square root of negative 1 is I. And then that's all being divided by 24. So now, just like the last problem, let's break that up into two separate fractions. Negative 8 over 24 plus 2i times the square root of 5 over 24. And then let's simplify both fractions. For the first fraction, 8 goes into numerator and denominator. 8 goes into negative 8, leaves us with negative 1. 8 goes into 24, leaves us with 3. So the first fraction simplifies to negative 1/3. The second fraction, 2 goes into 2 once, and 2 goes into 24 12 times. So we have plus 1 times the square root of 5, that's the square root of 5, over 12 times that I to give us our simplified complex number answer. Now let's solve a quadratic equation. The suggestion here is a square root property, which makes sense. The left side is a perfect square, so we can take the square root of both sides of this equation to get closer to our answer. So we'll take the square root of the left side, because squares and square roots are inverse operations. That's going to eliminate the square. We'll also take the square root of the right side. Every number does have two square roots, so that's why we have a plus or minus on that right side. On the left side, square root of that square is just the 9x plus 5. And on the right side, square root of 36 is 6, so we get plus or minus 6. Now because we don't have a radical at all on the right side anymore, I'm going to go ahead and write this as two separate equations. One, we'll say 9x plus 5 equals negative 6. and the other will say that the 9x plus 5 equals the positive 6, and then we'll solve both equations. Subtract 5 from both sides, and we'll have 9x equals negative 11. Divide both sides by 9, and we get x equals negative 11 ninths. In the other equation, subtract 5 from both sides, we get 9x equals 1, and divide both sides by 9, x equals 1/9. So there's our two solutions. This problem's asking us to find the constant that we would add to this binomial so that it becomes a perfect square trinomial. In other words, we're trying to complete the square. So to complete the square, we look at the coefficient of the linear term. That's the x term. We take that number, the 11, and we do two things to it. Divide it by 2, that gives us 11 halves, and then take that 11 halves and square it, and we get 121 fourths. That's the constant that we would have to add to this so that we would have a perfect square trinomial. Now if we did that, we would have x squared plus 11x plus 121 fourths. That's not equivalent to the original polynomial, but it is a perfect square trinomial, which we can factor into a binomial that's been squared. For the first term in the binomial, we're going to get that from the x squared. X times x is x squared, so that's the first term in our binomial. And for the second term, all we have to do is look back at what we got when we divided that linear coefficient by 2. We got an 11 halves. That's going to be the second term in our binomial when we factor our perfect square trinomial. The next problem says to solve the equation by any method that we choose. If we had a 0 on the right side of the equal sign instead of a 2, we could just use the zero product property. Unfortunately, we don't have that. We've got the 2. So let's put this in standard form by multiplying the two binomials on the left side first. So 4x times x is 4x squared. Outers 4x times 1, that's 4x. Inners 3x, or 3 times x is 3x. And last times last, 3 times 1 is 3. Equals 2. So let's combine some like terms. 4x squared plus 7x, and let's subtract this 2 from both sides, plus 1 equals 0. Now, if this would factor, that would be a simple way to get to a solution. This one isn't factorable, though, and I wouldn't waste a whole lot of time trying to factor it. If you don't see how to factor it fairly quickly, then it's probably not factorable. Don't waste a lot of time on it. So we're down to either completing the square or quadratic formula. Completing the square would be a little awkward because, first of all, we'd have to be dividing everything by this 4. It's multiplying the x squared, and then we'd have a fraction for our linear coefficient, which would give us kind of an unwieldy number to add to both sides to complete the square. So best bet's going to be quadratic formula. So for the quadratic formula, we need to figure out the a, b, and c. A is the 4, b is the 7, c is the 1. And so our solutions are given by negative b, negative 7, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So now we've just got a little bit of simplification to do. So we've got negative 7 plus or minus the square root of 49 minus 16 all over 2 times 4 is 8. So that's negative 7 plus or minus the square root of 33 over 8. There aren't any perfect squares in 33, so we're not going to be able to simplify this anymore. That's our two solutions. This equation asks us to solve it by factoring and using the zero product principle. So, in order to do that, we need to have a zero on one side of the equation. So we will leave our variables on the left side, our x cubed, our x squared, and let's subtract that 16x from both sides and also subtract the 16 from both sides. That gives us the zero that we need. Now let's group the first two terms together, and then let's group the last two terms together. We've got to be a little bit careful if there's a negative third term here. We don't want to lose that negative sign, so I'll do that by saying plus a group that contains negative 16x and negative 16. In the first group, there's a common factor of x squared. If we factor that out, that would leave us with x plus 1. In the second group, there's a common factor of negative 16. And if we factor that out, that leaves us with x plus 1. Now we've got common factors of x plus 1 in both of the terms we've created. So we'll factor out the x plus 1 and take that times the leftover factors in the two terms, which are the x squared and the minus 16. The x squared minus 16 is the difference of two squares, so we can factor that into x plus 4 times x minus 4. And now we're ready to use that zero product principle. Since we have three factors that multiply to give us 0, at least one of them has to be a 0. So either the x plus 1 is a 0, or the x plus 4 is a 0, or the x minus 4 is a 0. So we've got three solutions. X is negative 1, x is negative 4, or x is positive 4. Now this problem says to solve it by making an appropriate substitution. So I'm going to think that maybe we can do this by factoring if we're careful. So for example, maybe this factors into a binomial times a binomial. If I think about the x to the fourth power, that's x squared times x squared. And then I'm going to think of two numbers that multiply to give me 225, but add to give me negative 34. Those numbers are pretty big, so it's not real obvious what I'm looking for. So one little trick that we could do is look at that 225 and make a factor tree. Think of numbers that multiply to give us 225, like 5 times 45. And then 45 is 5 times 9. 9 is 3 times 3. I could go a little further with that, but I think I'm going to stop because I'm noticing 5 times 5 is 25. And I know that 25 plus 9 is 34. So what if I make this x squared minus 25 times x squared minus 9? Negative 25 times negative 9 would give me the 225, and 25x squared plus negative 9x squared would give me the negative 34x squared. So yeah, that's it. All right, so now each of those factors is a difference of squares, so we can factor those a little further. X squared minus 25 is x minus 5 times x plus 5. X squared minus 9 is x minus 3 times x plus 3, and we know at least one of those factors is a 0, so we can get our solutions from each factor. So either x is 5, or x is negative 5, or x is 3, or x is negative 3. To solve the equation with rational exponents, what we can do is raise both sides of this equation to the same power. Now the power we're going to choose is the reciprocal of the power that we see on the left side. So the reciprocal of 5/2 is 2/5. So we'll raise both sides of this equation to the 2/5 power. Now we're choosing that power for a very specific reason, and it's because of properties of exponents. On the left side we have an x minus 6 raised to a power raised to another power. When we raise a power to a power, we multiply the powers, and 2/5 times 3/2 is 1. So the left side is x minus 6 to the first, or just x minus 6. And on the right side, we've got 243 to the 2/5 power. So we might want to think about what that means. 243 to the 2/5 power is the 5th root of 243 squared. 243 is 3 times 3 times 3 times 3 times 3. So 243 is 3 to the 5th power. We're taking the 5th root of that, which is 3, and 3 squared is 9. So x minus 6 equals 9. Add 6 to both sides. X equals 15 is our solution. Now let's solve an absolute value equation. First step is going to be to isolate the absolute value. So we'll subtract 7 from both sides of the equation. So we get 3 times the absolute value. Subtract 7 from both sides equals 27. And then we can divide both sides of the equation by this 3 that's multiplying the absolute values. So if we divide the left side by 3, we'll just have the absolute value left. If we divide the right side by 3, we'll have 9. Absolute value is a distance from 0, so we're looking for what's in the absolute values to either be 9 units to the left of 0, which means what's inside the absolute values would be sitting down at -9, or what's inside the absolute values is 9 units to the right of 0, which means it's sitting down at +9. So now we've got two equations to solve. The first equation, we'll subtract the 6 from both sides, so we'll have -3/2 x equals -15. And then we'll multiply both sides by the reciprocal of -3/2, which is -2/3. And we'll get x equals, let's see, 3 goes into -15, -5 times -2, that is +10. And the other equation, we'll subtract 6 from both sides. We'll have -3/2 x equals 3. And then we'll multiply both sides of this equation by the reciprocal of -3/2, which is -2/3. And we get x equals -2. So there's our two solutions, 10 and -2. To solve the compound inequality, we need to use inverse operations to get the x by itself in the middle. The first thing we need to do is add 1 to all 3 parts. So we'll add 1 to the left part, the middle part, and the right part. So that's going to give us 0 is less than 2x is less than or equal to 10. And now we'll divide all 3 parts by 2. Since we're dividing by a +2, those inequality signs stay pointed the same way. If we were dividing by -2, we'd have to flip those inequality signs around. So 0 divided by 2 is 0, is less than x, which is less than or equal to 5. If we write that in interval notation, we would say that 0 is our left bound, 5 is our right bound. We don't want to include the 0, but we do want to include the 5. Now we've got an absolute value inequality. So step 1 is isolate the absolute value. It's been done already. Second step is to say that what's inside the absolute values is within 3 units of 0, within because of the less than. So that means that the 2x minus 7 is between -3 and +3. We'll add 7 to all three parts, and we'll have 4 is less than 2x, which is less than 10. And then divide all three parts by 2. Once again, it's a +2, so we don't have to flip the signs around. And we get 2 is less than x, which is less than 5. In interval notation, we would say that our numbers for x are between 2 and 5. We are not including either one. For this absolute value inequality, our absolute value is isolated, but now we are greater than 1 unit from 0, which means either our 1 minus 1/3 x is to the left of -1, or our 1 minus 1/3 x is to the right of +1. So let's solve both of those inequalities. We'll subtract the 1 from both sides, and we'll have -1/3 x is less than -2. And now we're going to multiply both sides of this inequality by a -3. Because we're multiplying by a negative number on both sides, we have to flip the inequality sign around to keep a true statement. So for this inequality, we have x is greater than 6. For the other one, we'll also start by subtracting 1 from both sides. So we'll have -1/3 x is greater than 0. Once again, we're going to multiply both sides of the inequality by a -3 to solve for the x. And because we're multiplying by a negative number on both sides, that inequality has got to flip around. And we get x is less than 0. So our solution is that either x is greater than 6 or x is less than 0. If we were going to graph that solution on a number line, we would say that x is greater than 6 would be all the numbers to the right of 6. And x is less than 0 would be all the numbers to the left of 0. And that can help us figure out what the interval notation should look like, because we've got two pieces on our number line to describe. The one on the left is all the numbers from -infinity to 0, not including either one of those. We can never get to infinity or -infinity, and 0 is not included. Union for the or, everything from 6, but not including the 6, to +infinity, but remember we can't reach +infinity, so we use parentheses to show that.